sigmoid function is one of the most famous functions in the field of data science and machine learning. It's particularly famous for its use as an activation function in a binary classification setting where we want to predict probabilities of something being true or not. For example, let's assume you have an image and you want to predict if this is an image of a cat or not. How will you go about this? One way to do it is to take all the pixels in the image and vectorize them into this one very tall vector x, which represents each and every pixel in the entire image from pixel 1 all the way to the last pixel m by n, where m and n are the elements of are the dimensions of the picture. So each element in this long vector x will be the value of x at pixel 1, value of the pixel at location 2, value of the pixel at location 3, and value of the pixel at the last location. Usually those values are between 0 and 255 for grayscale images. Once you have formulated your input and vectorize it, now you're going to pass it into our image classification, binary classification model. I'll call this the cat classifier. Cat classifier, which will take a vectorized representation of a cat, this tall vector, and it will generate an output that says yes cat or no, it's not a cat. Okay, how will that happen? Well, simply it will do a linear transformation of the input with the weights. So we have a weight vector here, w, which is equal to w1, w2, w3, all the way to wm times n. So we're going to do a linear transformation, w transpose x, which is a dot product between the vector w transpose and our input vector x. This is a dot product. It will generate a scalar value. We'll call that z. Z could be something like 2, it could be -1, or it could be something like 3, 5. It's a scalar value. And if your model is trained properly, the larger the value of z is, the more confident you are that this is a cat. And the less the value of z is, the less confident or sure you are. So if z is equal to 3, you are more confident than if z is equal to 1 or -1. But the problem is, what is the right threshold to use as your binary decision boundary between a cat or a no cat, between a yes and a no? Should 3 be that threshold? Should 2 be that threshold? Well, one way to do it is to try different values for the threshold and see which one generates the best accuracy. But in practice, that's not very intuitive. What is intuitive is to deal with something like a probability. I am 90% certain it's a cat. I'm 20% certain it's a cat, which means it's unlikely to be a cat. So is there a function that would take those outputs and convert them into probabilities? Yes, and that is exactly the purpose of the sigmoid function. So what the sigmoid function does is that it takes those scores, 3, 2, -1, whatever, which is the result of w transpose x. By the way, here I have ignored the bias term purposefully. You can just assume that I have included the bias term into the w just for ease. Okay. So the sigmoid function takes this score z and it converts it into a probability p that is between 0 and 1, which is something that's intuitive and easy to understand. Okay, so how does this sigmoid function do it? This is how the sigmoid function looks like. It is 1 over 1 plus e to the negative z. Okay, this is the equation of the sigmoid function. So for example, if you have a score of 2, it will be 1 over 1 plus e to the negative 2, which is something like 0.88. If this is how the sigmoid function looks like graphically, the squiggle, it is bounded from 0 from below and bounded by 1 from above. So it's between 0 and 1, which means it's always positive between 0 and 1. So it provides a probability-like distribution. So what will a z of 2 give us here graphically? Z of 2, if we follow the graph, it will be something like here again 0.88, which means you are 88% confident that this is a picture of a cat. Unlike having a low score like something like -1, which will result in a probability give you a p of 0.27, something like 0.27, which means that you are only 27% sure that this is a picture of a cat, which means it's unlikely to be a picture of a cat. So using the sigmoid function, we were able to convert scores that are unintuitive to very intuitive probabilities. And then you can just come here and put a threshold value of 0.5, for example, and say anything above 50%, I will say that it is yes, a cat. Anything below, I will say no, it's not a cat. And that is your binary classifier. And based on your application, you can move this threshold line up and down as you like. That's it. That is how to implement a binary cat classifier. Okay, I don't know what happened to my voice. Have a binary cat classifier. Okay, so one thing I have glossed over while computing all of these nice computations and how to go from a score to a probability was that I ignored defining what the weight value is. I just glossed over it. I assumed that we already have a pre-trained model that has an optimal set of weights. But what happens in practice is that we need to train, we initialize this weight vector, for example, at random, and we need to train our function or our network to find the best and optimal set of weights for the highest accuracy. And to do this, we need to understand how will the output probability or how will our prediction change for a slight change in the input. We need to know this because we need to know how to change the weights in order to find the best prediction. So we need to know what values of W that are optimal. So to do that, we need to find how does W impact the output or the prediction. And if you've watched our previous video on matrix calculus, I will link it in the description. We know that to measure the change in the output with respect to the input weights, this is nothing but the gradient. The gradient measures what will be the change in the output or how will the prediction change for a slight change in the weights or the input. So that's nothing by partial B by partial W. Okay, so what is partial P by partial W? That is nothing but the gradient of the sigmoid, right? Partial B by partial W is what's P? P is P is nothing but the sigmoid of Z, so it's nothing but the gradient of the sigmoid function. Z is nothing but W transpose X. Okay, so we need to compute this partial derivative of the sigmoid function. How do you determine the derivative of the sigmoid function? That is the topic of our next slide. So, as we know, our sigmoid function is 1 over 1 plus e to the negative z. And I can jump straight ahead and tell you that the gradient of the sigmoid, I'm representing the gradient with this prime sign here. So the gradient of the sigmoid is nothing but the sigmoid itself multiplied by 1 minus the sigmoid of Z. Okay, so the gradient of the sigmoid is the sigmoid times 1 minus the sigmoid. This is a very important and easy derivative to remember. And if you don't want to know how this is computed, you can skip straight ahead. If you're interested to know how this gradient is computed, we're going to compute it in this slide. Okay, so let's do it. What is the gradient of the sigmoid function? So what is the derivative of 1 over 1 plus e to the negative z with respect to z? Well, using the quotient rule, 1 plus e to the negative z will be 1 plus e to the negative z squared and multiplied by -1 times the derivative of what's inside. That will be the derivative d by dz of 1 plus e to the negative z. Take a minute to convince yourself that this is true. If you don't know how to do the quotient rule, just take this denominator here up. It will be power -1. Then do the usual derivative, take the -1 down, and then subtract 1 from the power. It will be -2. And then bring it back to the denominator, it will be power 2. So it's -1 times 1 over 1 plus e to the negative z squared times the gradient of what's inside. Okay, so what's the gradient of 1 plus e to the negative z? That is nothing but e to the negative z times negative 1, which is negative e to the negative z. So the negatives will cancel out, which means that the gradient of the sigmoid will be 1 over 1 plus e to the negative z squared times e to the negative z. Okay, let's do another step here. How is this term equivalent to this term? Let's see. We will do a very simple trick here. We will expand this 1 plus e to the negative z square into 1 plus e to the negative z times 1 plus e to the negative z. Those two terms are equivalent, times 1 times e to the negative z. Okay, now we're going to take 1 over 1 to the e to the negative z outside. So this will be 1 over 1 plus e to the negative z multiplied by e to the negative z over 1 plus e to the negative z. Okay, we're almost there. We're just gonna apply one last trick, which is we're gonna add 1 and subtract 1, which means we've done nothing. We've added 1 and subtracted 1 from the numerator. But this was a very smart trick, because now the gradient of the sigmoid function will look like this. 1 over 1 plus e to the negative z multiplied by e to the negative z plus 1 over 1 plus e to the negative z, which is this term here, minus 1 over 1 plus e to the negative z, which is this term. Okay, as you notice, 1 plus e to the negative z and 1 plus e to the negative z will simplify to just 1. So the final gradient of the sigmoid function is 1 over 1 plus e to the negative z multiplied by 1 minus 1 over 1 plus e to the negative z. And as you can see, that is nothing but the sigmoid itself, right? The sigmoid is 1 over 1 plus e to the negative z. So the gradient of the sigmoid is the sigmoid times 1 minus the sigmoid. The sigmoid times 1 minus the sigmoid. And this is how you prove that the gradient of the sigmoid function is the sigmoid times 1 minus the sigmoid. So if you don't want to go through all of this hassle, just memorize it. And that's what I do. It's a very useful gradient to memorize. Okay. Now that we have proven the gradient, let's talk about some functions or some properties of the gradient. So as we know, the sigmoid function is bounded from 0 to 1. It's always positive, and it saturates at both ends. And because it saturates at both ends, the gradient of the sigmoid, which is sigmoid times 1 minus the sigmoid. If you plot this function here, it will be this red dotted line, which, as you can see, because the gradient saturates, the gradient is basically the slope, right? So the slope is maximum at here, and then it starts to slow down until it becomes almost 0, almost 0, almost 0. So the gradient or the slope of the sigmoid function dies at the extremes here, right? It becomes almost 0. So it's maximum when the score is 0, and its value here is 0.25. And it dies or approaches 0 on both ends. This is a very, very important property of the sigmoid function to remember, that the gradient of the sigmoid function dies at the extremes or approaches 0 at the extremes. And this will be a very, very critical thing to know, because that's why we do not use the sigmoid function in very deep neural networks, because the sigmoid function has a dying gradient, which means it will make it very difficult for learning. More on this to come in next videos, in future videos, so stay tuned. But all you need to know for now is that the gradient of the sigmoid function dies at the next video. We will see how to compute a vectorized representation of this gradient. So this gradient is the gradient of the sigmoid function when z was a scalar. We've assumed that z is something like 2, 3, minus 1. But what happens when z is a vector? z1, z2, all the way to zn. We will see when will this be the case and how to compute this gradient. This will be the vectorized implementation of the gradient. Until then, if you find this video helpful, don't forget to smash the like button on your way out, and see you in the next video.